Yeah, the recording has been started now. So you will have 3 lectures and 1 tutorial class. So we will have to assign the tutorial class by asking you. So whenever you are free in the chat box, kindly inform us the slots which are already booked. Okay, from those of which uh, are free, we will book one slot. We are 2 tutorial teachers for you, me and Dheeraj Patel, who is in the meeting. Our IDs are available to you for contact, right? The main contact platform would be our institute email ID. So if you have any trouble, thank you, Naveen, for informing us that some slot, what are the slots that are booked now. So because we are running late, I'll try to move on in a fast pace. Okay, so in this course, the prerequisite is actually a basic course in function. The prerequisite for this course is actually a course on calculus. Plus, you should be able to understand a basic level of rigor in mathematics. Okay, a basic level of proof. Please, please. So if you have any questions, then you can unmute yourself and ask. Otherwise, kindly keep yourself muted. Okay, this is a humble request. If you have any questions, only then unmute yourself. All right. So, um, in any course on basic course in mathematics, you will always study some properties of a set endowed with some structures. So in calculus, you have seen that you have real number system, which we say by R. We were studying functions on R, right? And then we used to study its various properties, right? So a natural progression for this is metric spaces. I guess most of you are familiar with metric spaces in your undergraduate courses. If not, then it's okay. You just need to like have a look beforehand all the lecture notes which are provided to you. Okay. In the metric spaces, you will not have real number system. You will have a set endowed with a distance function. You will study functions on this particular set and related properties. And its natural progression is topological spaces. Okay, here we also have a set and with some specific structure, which I won't say now because it will be later in the course. With some specific structure, again we will have functions there and properties of these functions and these sets. Fine. So this week is particularly for preliminaries. We will just discuss some preliminaries. As you have seen in the lecture notes, if you are able, if you were able to access that before, that these are nothing but just some specific preliminaries from set theory. Okay, so we have Zorn's lemma, axiom of choice, well ordering principle, countably well ordering principle of natural numbers, which we denote by n, countability uh, and uncountability. That means countable and uncountable sets. Fine. So today we will start by relation. A relation is actually a most basic way of giving structure to a set. Okay, so in particular, if we have definition, we define in the following way. If we have X to be a non-empty set, then any subset of X cross X is called a relation. Any subset of X cross X is called a relation. Okay, so some clarification is required. So if R is a relation, that means if R is a subset of X cross X, we usually say X R Y if and only if X Y belongs to R. Okay, we use R for two symbols. Fine. Now it is in fact a binary relation because we assign to every we are taking a subset of X cross X. Okay, please inform us about the course policies related to major, minor, and quizzes. Thank you for asking this. So I think the course policy was already mentioned in the mails by Professor Kundu sir. We will not have any quizzes. We will have only one minor exam and one major exam. And weightage is 40% and 60%. That means you will have uh, an exam, minor exam, which will be of 40 marks, and a major exam which will be of 60 marks. And when will this exam will happen? You can see this in the academic calendar provided by the institute. If you go to IITD website, there is an academic calendar option there. From there, there are some days fixed for these exams to happen for every course. Okay. Anything else? Okay. If no one
No,
has
ma'am. And the quizzes.
oh, what? Sorry, I don't understand. Hello.
No issue,
Ma'am,
ma'am.
what
You can
about
continue.
quizzes?
Okay, please continue
Only two
this.
tests will be held,
Yeah, only two tests will be
major
held.
and minor.
Major and minor. Major 40,
Okay,
minor
ma'am.
40 marks, major 60 marks. It's already in the mail. Okay, right. So we were
Okay,
talking
ma'am.
about relations. It is precisely a binary relation because we are taking x twice, right? We are taking x twice. So this is actually a binary relation. For now we can see some examples. Suppose the set is R. I say X is any point in real numbers. X is related to Y if and only if X is equals to Y. This is a subset of R cross R, so it is also a relation. I can also say that X is related to Y if and only if X is less than equals to Y. Okay, that is also a relation. I can more examples. If I take up say a non-empty set X not equals to 5, I can take its power set. On its power set, I can define a relation. How? Let suppose I take two subsets A and B. So I say A is related to B if and only if A intersection B is equals to 5. This is also a valid relation. I can say that A is related to B if and only if A is contained in B. This is all these are valid relations. Okay. So next we have specific types of relation which are important. Okay, we have equivalence relation and partial order. Fine. So these two are important types of relation, and in order to define this, we need to understand four subtypes. that is relation of reflexivity. So we say that a relation is reflexive if and only if every element is related to each itself. Okay, so if x is related to x for all x in the particular set, then we say that this relation is reflexive. So let's quickly come to the examples. So these are the examples, right? So just quickly tell me, if obviously equality relation is reflexive because every element is equals to itself, right? I In the second example also, if x is always less than equals to x, so this is a reflexive relation. But if you see the third example, if I take a non-empty subset, a non-empty set, sorry, if I take a
Intersection
non-empty,
A equals to A.
A intersection A is always equals to A, which is non-empty for any non-empty set A, right? So this relation 3 is actually not reflexive. Okay.
Yes,
And
sir.
the fourth one, if A is contained in B, this is also reflexive. Fine. So next type is symmetry. So we say a relation is symmetric if x is related to y, then other way also holds. Then this should imply y is related to x. Okay, so it's a condition. If something is related to something, then opposites should also hold. So coming back to the examples, you can quickly see that this relation 1 is symmetric. Can you tell me if 2 is symmetric?
No, ma'am.
No.
No, definitely
No,
no.
ma'am.
No,
3,
ma'am.
No, ma'am.
3 is
No,
symmetric.
ma'am.
3,
Symmetric.
No,
3 is,
ma'am.
Symmetric.
3 is
Symmetric.
symmetric. If A
Yes.
and B are disjoint, then B and A are also disjoint.
Also genuine.
Okay, and
Yes, ma'am.
this one is also not symmetric.
Not
Fine.
symmetric.
The next one is antisymmetric. Okay, antisymmetry. We say a relation is antisymmetry if x is related to y and y is related to x, then this should imply that x and y are equal. Okay, so it's different. Now if I see this in this particular example set, antisymmetry, so number one is actually antisymmetric itself,
Yes,
right?
ma'am.
Number two is also antisymmetric
Yeah,
because
symmetric. Okay.
fine. Number three, antisymmetric or not?
No. No.
No,
Very good,
ma'am.
very good,
No,
very good.
ma'am.
And number four is also antisymmetric because if, yeah, so very good. Next one is what? Transitivity. Transitivity means that if we have x related to y and y is related to something else, say z, then x and z should also be related. If this holds, then we say that x and z are related through the transit of y. Okay,
Okay.
it is x related to y and y related to z. This should imply x is related to z. Again, in this example, this is transitive. This is also transitive. Is 3 transitive?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Very good.
No, ma'am.
You
No,
can
no,
take,
no, ma'am.
suppose these are the sets.
No, ma'am. It's not.
Yeah, these are disjoint, but these are not disjoint. If this is A, this is B, this is C, definitely no. Third, it is also transitive. Okay, so you see that in the particular example one, it satisfies all these properties. Okay, some satisfy some and some does not. In general, we say that a relation is an equivalence relation if it satisfies reflexivity,
Transitive.
symmetry and transitivity. Okay, reflexivity, symmetry, and transitivity. So a very special example I would like to introduce in this situation is about rational numbers. Okay, so another example I want to introduce is the rational numbers. So we were introduced to rational numbers as uh, integer divided by an integer, right? Which and the numerator denominator is non-zero. So I can say if I take this set as z cross z minus 0, and if I define a relation on this one, that a tuple AB is related to CD if and only if A by B is equals to C by D. Okay, then this is also an equivalence relation. And if you see that 2 by 3 is actually equals to 4 by 6, right? And we do not differentiate this. So you see one particular function and all the elements which are related to this function are disjoint from say 5 by 7 to another class. Okay, so either you see that equivalence. Okay, sorry, I didn't said what is an equivalence class. I'm sorry. An equivalence class is a subset of X which collects all the elements which are related to that particular set. Okay, I'm sorry, I didn't define an equivalence class. An equivalence class, if X is in X, we say equivalence class, we denote it by this bracket X, and it collects all the elements in X which are related to X. Okay, so you see this particular sort of relation, that is an equivalence relation, actually partition the set X into pairwise disjoint sets. That is either equivalence class of X is equals to equivalence class of Y, or they are disjoint. So this in fact form a partition of X. And suppose if we are given a partition of X, then we can always define a relation so that it becomes an equivalence relation. So the equivalence relation is nothing but actually a partition of X. Okay, so in this way equivalence relations are important. Next we study partial order. A partial order is a relation which is reflexive, antisymmetric, and transitive. So if you see the second example is the partial order. The fourth example is also a partial order. So if you see, we have some sort of ordering. We are calling this partial because we, in particular, two elements may not be comparable. We will say that our two elements are comparable if either x, sorry, if in the particular case when a relation is a partial order, it is convenient to write that relation to be a less than equals to. It is a notation. Okay. We will say that x is less than equals to y if y x is and y are related. Okay, and that satisfies reflexivity, antisymmetry, and transitivity. Okay, so why is a partial order important? So in partial order, we have a certain order on the set. Okay, it will behave like the less than equals to ordering of the real numbers. But in real numbers, we actually know that any two elements are related. In a partial order, in general, two elements may not be related. That is, two elements may not be comparable. As an example, I would like to say that if we have a finite partial ordered set, in short a PO set, then we can always use a diagram to denote this. So for example, if I have a set A, B, C, D, and if I define a relation A, B, C, D, this diagram means that D is less than equals to C, D is less than equals to A. That means Any elements below is related to any element above related by the line. Okay, D is less than equals to B, and C is less than equals to A, C is less than equals to B. So if you see, we can finite posets are easy to denote by diagrams. So in this diagram, you see A and B are not related, but we still have some sort of ordering in the set X. Okay, so if every element of the set is related to each other, then we say that the poset is actually a chain or a totally ordered set. Okay, if I just take this particular relation, this particular subset of this set, then this set is actually a chain in X. Okay, now I'll define upper bound. So an upper bound of a poset is actually something. Suppose we have a non-empty subset of X. Suppose we have a non-empty subset of X. We call U in X to be an upper bound of Y if U dominates every element of Y. That means if Y is less than equals to U for all Y in Y. Okay, U is trying to dominate every element of X. Therefore, we call this an upper bound of Y. Fine. So if you see in this particular example, if I take this Y, then both A and B dominates this particular Y. All right. So both A and B are upper bounds for Y. Fine.
Yes.
Next, we have a notion of maximal element. Actually, a maximal element is one which is not dominated by any other element. Okay, maximal element is the one which is not dominated by any other element. That means if some we will say that M is a M in X is a maximal element of X, sorry, in X if X, if M is less than equals to X, that means if something is bigger than X, then this should implies that M is equals to X. That means we have nothing bigger than M in the set. So again, if I in our particular example, this tree, if you see, A is also a maximal element of the set because nothing is above it. Okay, nothing is above it. Therefore, A is a maximal element. But similarly, you can see that nothing is above B. So B is also a maximal element. Okay, do you understand?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes.
So
Yes, ma'am.
next is Zorn's lemma. Zorn's lemma is actually a very powerful tool in mathematics. It actually shows, it's a method of showing existence of something. Okay, existence of what? It will be clear with the statement. Zorn's lemma actually says that if every chain in a post set, that is partially ordered set, has an upper bound. Okay, if every chain has an upper bound, then then X must have a maximal element. That means at least one element is there who is not dominated by any other element. Then X has a maximal element. Fine. So let me give you an example. You remember our example number 4. We were taking a power set of a non-empty set, and we were saying A is related to B if and only if A is contained in B. We saw that this is actually a poset. So we can denote it by less than equals to. That means the power set of this particular set X with containment is a poset. Fine. Is it fine? Now suppose
Yes,
I
ma'am.
take X is A, B, C. So I can say phi is a particular subset of A, B, C. So I'm again using a tree diagram to denote this poset. Fine. We have AB, BC, AC. Fine. We have some sort of structure like this. And then everything is contained in ABC. So if you see, if I remove this from this particular poset, if I just take this as a relation, then you see that this particular poset has 3 maximal elements, right? And if I take the complete one, then you can see if I take any chain, whether I go this way or this way or that way or that way, if I go anyway, every chain has a maximal element that will be actually the whole space X. So this one is not specific. If I take this as a poset, then the particular element X itself is in P of X is a maximal element. It is something which is also an upper bound for any chain in this itself. Okay, so it is easy to see in this one, but Zorn's lemma say that in particular you take any poset in which every chain has an upper bound, then this X has a maximal element. This Zorn's lemma has particularly many applications in analysis, whether that be in linear algebra in proving that every vector space has a basis, or Hahn-Banach extension theorem, which is crucial to any course on functional analysis. This particular lemma, which sees to be a very simple statement, is very powerful. Now, one word on that, this lemma is actually should not be called a lemma. There is still no proof in the literature which proves this statement. Okay, this is therefore it is actually an axiom. It has no proof in the literature. We just assume that this statement is true. Okay, so does
So
anyone
why we are calling it lemma?
so that is actually a historical that has historical roots there. So why we are calling it a lemma, you can actually use internet. Okay, we have no proof,
Okay.
but it is equivalent to many things, and it is crucial in proving many important existence theorems. I'll again remark that it only proves existence. It will not say how many maximal elements will be there. We see that in this example there were 2 maximal elements. It says that there will be at least one. So does anyone remember the proof where we showed that its application, that every vector space has a basis? Does anyone remember?
Yes.
Yes,
Yes, ma'am.
ma'am.
Yes, ma'am.
Okay, very good.
Yes, ma'am.
I'll just recall this one. In
Ma'am, finitely generated vector space.
uh, please unmute now. Okay. The finitely generated, it's not finitely generated. I'm saying every vector space has a Hamel basis. Okay, any vector space has a basis. Finitely generated, infinitely generated, whatever it is. Okay, so in proving that there will be at least one basis, Zon's lemma is required. I'll just state the idea of the proof. We just take, suppose V is a vector space over F. F is a field here. So the poset which we will take is, we will take X to be the poset, the set to be, we will say any element is in X if it is a linearly independent set of vectors in V. Set of all linearly independent. I think you all know what is linearly independent by now. Linearly independent. Yeah. Set of all linearly independent vectors in V. So if you see any particular set of linearly independent vectors here, then oh, actually it's 12:48. So I think you should just try to revise it yourself. If you see that, if you feel that Zon's lemma is not useful in proving this theorem, then kindly tell me in the next class or maybe in the chat box what is, what you feel is important. Okay.
Okay, ma'am.
Okay. So next is the concept of countability and uncountability. So countable sets and uncountable sets are actually a type of measure of size of the sets. Okay. So we say a set is finite if, okay, if we have a natural number n, so that x can be put in a one-to-one correspondence with the set 1 to n. We say x is a finite set. Um, One thing I want to ask is the handwriting clear?
Ma'am, so
Yes, ma'am.
Yes, ma'am. No, ma'am.
No. Should it?
Ma'am, please write big, small.
It's small. Okay, fine. I'll try to write big now. You should have informed me beforehand. Okay, I'll try to take care in the next class or any other tude. We say we say X is a finite set if there exists a natural number, that means n in n, such that we can put X in a one-to-one correspondence, such that X is in a one-to-one correspondence with the set 1 to n. Okay, 1 to n. One-to-one correspondence is actually a bijective map. That means a map which is both 1 1 and onto. I think this one you should know. Fine. So
Yes, ma'am.
yeah,
Yes.
a set which is not finite will be called infinite. Now in the infinite sets, we have n is also infinite, the set of natural numbers. R is also infinite, the set of real numbers. They both are infinite, but R, you can feel that it is intuitively something much larger than n. Okay.
Yes, ma'am.
R, we know that n we can enumerate as 1 2 3 4. It has something which is smallest. But if you take real numbers, nothing is smallest. If we have n there, its next bigger element, its successor is actually n plus 1. But we have no successor in the set of real numbers. So R we can think as intuitively a larger infinite set then the natural numbers. Okay, so this way we define a set to be countable if it is something similar to natural numbers. That means if it is, we know that it is infinitely large, but n is something smaller infinite set. So if we have something a smaller infinite set, then it is countable. How would we say that? The definition is that countable set. So X is called a countable set if there exists a one-to-one correspondence f from natural numbers to the set X. Okay, fine. And if this holds, then we can actually list out the elements of X. We can actually list out the element of X as x1, x2, dot, 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 and so on. Okay, xi is basically here f of I. And this f is actually called an enumeration of X. Okay,
Okay, ma'am.
fine.
Okay,
And
ma'am.
so we have a set is actually now a smaller infinite set if it is countable and larger if it is not countable. And a not countable set is called an uncountable set. And by definition, an uncountable set is actually infinite. Fine. So we have many examples in the tute for it, this one. So if you see the tute sheet, are you able to see my screen?
Yes, ma'am.
Yes.
Yes, ma'am.
Oh, fine. Um, I think I cannot access this. It's okay. So in the tute sheet itself, we have the initial questions. I think question number 1 to 7 or 6 are whether a set is countable or not. Okay. So you please go and try that examples. Fine.
Yes, ma'am.
Okay, ma'am.
Hello.
Kumar Sharma, I think your hand is raised. You want to ask something?
यस मैम।
Please ask then.
मैम इसी जो रिलेशन है पोसेट्स में एक
Okay.
टर्म होती है आइसोमॉर्फिक, वन सेट इज आइसोमॉर्फिक टू अनदर सेट। तो मैम वो अगर आप थोड़ा बहुत समझा देंगे क्या होता है।
आइसोमॉर्फिक मैंने पोसेट्स में नहीं पढ़ा है।
मैम आपकी वॉइस बहुत लो आ रही है।
हेलो
हाँ जी।
हेलो, अब क्लियर है वॉइस?
यस मैम।
Yes, ma'am.
पोसेट्स के अंदर आइसोमॉर्फिक टर्म मैंने नहीं पढ़ा है। ठीक है, आई हैव नॉट स्टडीड एनी टर्म आइसोमॉर्फिक in relation to the term poset. There are many isomorphic terms in mathematics.
ओके
That's
मैम।
not,
मैं
if you
आपको
can, आप
एग्जांपल
मुझे एग्जाम्पल एक काम करिए, इसी चैट बॉक्स में उसका फोटो शेयर कर दीजिएगा।
ओके मैम।
ठीक है, बट अभी 5 मिनट बची है। आई थिंक बस मैं इस नोट के आई जस्ट टॉक अबाउट वेल ऑर्डरिंग प्रिंसिपल एंड प्रिंसिपल ऑफ मैथमेटिकल इंडक्शन व्हिच इज लेफ्ट फॉर दिस लेक्चर। ओके, so principle of mathematical induction, yeah, so well ordering principle, a well ordering principle actually says that, sorry, well ordering principle of natural numbers, it actually says that if we take any non-empty set of natural numbers if that means if we take any non-empty set of natural numbers, then it will have a least element. Okay, so before that I'll try to say what is a least element.
Ma'am, you are not audible.
Yes, ma'am, you are not audible.
Hello, hello.
Yes,
Yes,
ma'am.
ma'am. Now audible, ma'am.
Oh, okay, fine. I'm sorry, I didn't realize. Sorry. Just a word. A least element of a subset of n. Suppose S is a subset of n, non-empty. We say S has a least element k if k is less than equals to n for all n in S. Okay, it's very simple. Now clearly this S must be unique. K is unique. Sorry, this least element is unique. Well ordering actually says that every non-empty set of n is has a least element. That means there will always exist for every non-empty set of natural numbers, we will always have a least element. Now just go and try to think whether it's related to Zon's lemma or not, whether it is actually provable or not provable. Okay, because it's already time.
No.
I will not take further time. Okay, if any questions are left about this class, then please tell. Any general
Ma'am,
question about the course
ma'am, I
policy?
have a doubt.
Just one second.